Hello, let us do some problem solving on moment of inertia. Moment of inertia is one of these topics that gets introduced in statics, and you really see um, how it's applied and how it's used a little further down the road. All right, so let's start with some problems. So problem one, we need the centroid of a rectangle and then centroidal moments of inertia. So I've got a 1.5 by 3.5 inch cross section. So I've got a nice symmetric cross section. So my centroid is here using X and Y. Going from here to here is my X bar. From there to there is my Y bar. So X bar equals 3.5 divided by 2. That equals 1.75 inches. Right, so we could write by inspection or by symmetry in kind of an exam situation where you wanted people to follow your work. We can do a similar thing here for Y bar. So Y bar is the total height of 1.5. Divide that by 2, and we're going to get 0.75 inches. And again, we can just say that by inspection. All right, so those are pretty easy. For moment of inertia of a rectangle, you're going to want to memorize the formula base height cubed over 12. And we always interpret this, like there's always errors on, which term is it that I'm cubing. So the one you cube is always perpendicular to the axis you are investigating. So let's start with IX. IX equals BH cubed over 12. And so I've got a 3.5 and a 1.5. My centroidal x-axis is this one. So the one I want to cube is 1.5. Okay, inches to the fourth in the numerator, 12 in the denominator. And we can punch this through 3.5 times open parentheses 1.5 squared. I'm going to turn off actually my math print because I do a little better with classic mode. Okay, so 3.5 times open parentheses 1.5 cubed and close parentheses divided by 12. And we get the answer that's given to you here, 0.984 inches to the fourth. Moving on to the last problem to solve for what a IY is, the moment of inertia about the centroidal y-axis. So there's my centroidal y-axis. The one I want to cube is perpendicular to that line, so that would be 3.5. So 3.5 cubit times 1.5 inches to the fourth all over 12. Back to calculator. 1.5 times open parentheses 3.5 cubed divided by 12 equals 5 and change. So we've got our answer matching. 5.36 is fine for 3 sig figs here in our final answers. All right, remember to keep using these leading zeros. Leading zeros. Those are good to have. And yeah, it's how to report these answers. Let's go to the second problem. Okay, so do this one pretty quickly. We've got two different members that are glued together, but we do have, these lines of symmetry. So by inspection, X bar from here to here is equal to half of 3.5. That's 1.75 inches, which is what shows up above. Y bar from the bottom fiber to the centroidal x-axis, we call that Y bar, and it's equal to half of 3. So that's 1.5 inches, matching this here. Now time for moment of inertia. We have to do I sub x and I sub y. So again, what is the moment of inertia about the centroidal x-axis? What is the moment of inertia about the centroidal y-axis? And here's my x-axis here. And we know that our formula for a rectangle is bh cubed over 12. And we just have to interpret that to make sure we're cubing the right term. So for my centroidal x-axis, I want to cube 3 because it's perpendicular to that. So 3 cubed, the other dimension is 3.5. That's all in inches to the fourth, 12 in the denominator. I just put that in the wrong place. Let me fix that. Okay, so that one should go up there. All right, so moment of inertia about x is 3 is the one that we cubed there. So I go to calculator, 3.5 times 3 cubed divided by 12 is equal to 7.88 inches to the fourth, which matches the given answer up here. Let's do the y-axis. So here's my centroidal y-axis. Which do we cube? The 3.5. Right, 3.5 cubed times 3 divided by 12 equals 10.7. All right, that is number 2. Number 3. Same thing. So we're looking for the centroid x bar y bar and centroidal moments of inertia. And there's a little note that says, assume that this cross section and all the others are glued together, even when the glue isn't explicitly illustrated. So I did show kind of gluing and lamination for these first two, or for this first one here, and just didn't draw it in the other drawings. All right. These are going to be more involved because we're going to have a composite shapes. And so a little more work on our end for these types of problems. All right, well, our throwaway origin is over here, and we are looking for my centroidal axes. So you want to figure out where centroidal x is, where centroidal y is, and we're going to want to go from that origin to the x direction. I'm sorry, to the y-axis in the x direction for our x bar, and from the bottom fiber up to the centroidal x-axis to solve for what my y bar is. And we did this in the centroid unit, but it's been kind of a while, so this is that extreme bottom left fiber. And the nice thing about using that point, so the math would let you do what we're about to do about any point, any axis, but the nice thing about using that point all of the time is that all of your area is going to lie in quadrant 1 of the unit circle, like 2 and 3 and 4, that kind of thing. So we're gonna be working in quadrant 1, and so that's why you don't ever have to worry about signs when you're doing your centroid calculation. You can just look at magnitude. All right, let's go ahead and set it up. So centroid calculations are kind of a weighted average. We're always looking for lines of symmetry first to speed our work up. So I see a line of symmetry here, and so I can say by inspection, x bar is half of 3.5 equals 1.75 inches. Okay, so that one is very easy. Y bar, I've got to actually use the composite area method. And the composite area method says that y bar times the total area is equal to the summation of the areas times the distances. And sometimes you see people put a y sub I over here. I just like to do distance generic as d, but if you want to do y, that's totally fine with me as well. Another way that you would commonly see this equation is y bar is equal to the sum of the areas times distances over the sum of the areas. Okay, so we go into our cross section. I have area 1 and area 2. And area 1 equals area 2. All these are made with the same cross section, just gluing them together. It's a 2x4 piece of lumber, but even though this is like how we call the piece of lumber 2 inches by 4 inches, the actual dimensions are a little bit less. So 1.5 by 3.5. That's due to the way that the wood is seasoned as it goes from fresh cut green lumber until it's dry and kind of ready to use for these types of purposes. But okay. All right, so in the denominator here, we have quantity 2, and then I've got 1.5 times 3.5. That's all my area, and inches squared are my units down there. And now I just need areas times distances. So I'm going to call, I did already, so area 1 up here. So area 1, 1.5 times 3.5. And the distance that I want goes from this bottom fiber to the centroid of shape number 1. So I'm going to write that out as 3, not with that pen, 3.5 plus 1.5 divided by 2. All right, let me make myself just a bit more room here. Make this a little smaller and move it over. Okay, that should work. And continue in my numerator. Okay, so the first term I have is A1D1, and I need to add to it A2D2. Well, area 2 is 1.5 times 3.5, and distance 2 is from that reference axis here to the center of that component. So that vertical distance is going to be half of 3.5. And that numerator is all in inches cubed. I guess I'll see if I can condense space one more time. Okay, inches cubed. So in terms of my unit analysis, I have inches squared, inches cubed. So we're going to report our answer in inches here. Okay, calculator time. I tend to work these almost like backwards. So here's my procedure. I do like 3.5 divided by 2 times 3.5 times 1.5 equals plus 1.5 times 3.5 times open parentheses 3.5 plus 0.75. Okay, let me look at that real quick, make sure I've got everything good. Okay, that looks good. And then divide by 2, divide by 1.5, divide by 3.5. And I've often noticed that the way that I use my calculator is quite different than the way most of my students do. So I don't know if mine's better or worse, but it's just the habits I've developed over a lifetime of using it, and also using much simpler calculators a very long time ago. But that works for me, so use your own method if it works better for you. But we have got another of our answers ready to go. So y bar is equal to 3 inches. And I always like to give that a reality check. So if you look at kind of where we had guesstimated this centroid was, does that y bar look like, less than 3.5? Like we calculated at 3.0. And yeah, that makes good sense. So to give those little reality checks. All right, as we go into moment of inertia, I'm just gonna make this small. I'm gonna put it over here. Make this small too. Okay, that way I've got it if I need it for some reason later. I can buy myself a little real estate. All right, it's time to do our parallel axis theorem. And I'm gonna clean this drawing up a little bit. So here are the things that we know so far. We know our centroid is here. And so there's my centroidal x. There is my centroidal y. And in terms of area moments of inertia, these are the only axes that it's practical to do a moment of inertia about, okay? You can do a moment of inertia about other axes, whether it's this one, that one, right? Any line you can draw, you can calculate a second moment of area about that line, but these are the only ones that are practical and useful for engineering. All right, let us add a little information. So we calculated 3 inches from here to here. And if I take my total height of 5 inches, then from here to here, this little piece here is 5 less 3 less 1.5, and that little piece is 0.5. Okay, renumber the pieces 1 and 2, and I'm ready to do my parallel axis theorem. Let's do IX first. Moment of inertia about the centroidal x-axis. Parallel axis theorem says we need the summation of the moments of inertia of each component about its parallel axis plus the summation of the areas times the distance squared of all the components. We have 2 components. So for us, we could say I1 plus I2 plus A1 D1 squared plus A2 D2 squared. Moment of inertia. Okay, so we're looking at X. We're looking at X. So I usually don't draw this, but here's what I'm thinking. There's the axis about which I want the moment of inertia. So my parallel axes of shape 1 is that one, and shape 2 is that axis there. So we're going to start with those moments of inertia. I1. So moment of inertia of a rectangle, BH cubed over 12. And the one that I want to cube is perpendicular. So I'm going to do 1.5 cubed times 3.5, all that over 12. And next term, I sub 2. So base times height cubed divided by 12. So base, right, 1.5, height 3.5, cube it over 12. You never, ever, ever have any negative signs. All these are magnitudes, okay? Okay. Plus, you know what? Every time I ever make a strong statement like that, immediately I'm like, actually, there's an exception to the rule. So you would have negative signs if you were using solids and voids. If you're just using solids, then you won't have any negative signs. Okay, A1 D1 squared. I'm going to factor this out because A1 is equal to A2. So I'm going to factor out 1.5 times 3.5. And now I can just put D1 squared plus D2 squared in that bracket that I just opened up. I'm just going to make a little more room for myself. Okay. All right, so this is where a lot of mistakes get made. The distance that we want is from the center of the component to the centroidal axis that we're interested in, namely IX. So there is my perpendicular distance between the 2 parallel axes, thus the name parallel axis theorem, PAT. Okay, so that distance, I have my, let's see, from here to here is half of 3.5. And then I want to subtract out the 0.5. Okay, so 1.75 minus 0.5 gives me 1.25, and I have to square it. That's my D1 squared term right there. Okay, now I need my D2 squared. So center, oops, I just mixed them up again. Doing these videos is requires a lot of focus, more than I have today, apparently. All right, we just did D2. Backing up to D1, now we want the distance from that centroid to the x-axis. So here we're measuring the perpendicular distance between the parallel axes of component 1 and overall axis x. So for that distance, I want half of 1.5, 0.75 plus 0.5. That is also 1.25 squared. Isn't that funny? It's almost like I knew. All right, coincidence, complete coincidence that those numbers are exactly the same because of the problem dimensions I set up. All of this, so I want to just spot check my units. Right, so inches times inches cubed, inches to the fourth. Inches cubed, inches to the fourth. Inches squared, inches to the fourth. So just a little spot check on units there. And I'm going to go to my calculator. As I mentioned, my process is kind of backwards of the way that I usually see students do. So I usually start with the most complicated term and handle that first and then work my way towards the simplest term. So I would do 1.25 squared, double it, times 1.5 times 3.5 equals, okay, and then plus, open parentheses, 3.5 divided by 12 times, open parentheses, 1.5 cubed. Plus, and I'm ready for my last term, 1.5 divided by 12 times, open parentheses, 3.5 cubed, close parentheses again. And I get 22.75. This calculation, so I've done this before, so there's the answer. So I'm spot checking and making sure I don't have an error. But if I'm doing this on my own, I always do it twice. Always do it twice. And it's just so easy to make a mistake somewhere in that lengthy calculator operation. So strongly recommend that you do this twice as well. Okay, that was my IX. I'm gonna get some real estate. So I think I'm going to this. I keep the calc. Okay, I'll just put this over here in case I need it later. Get rid of all this stuff. Cut. Okay. And I can use this equation, parallel axis theorem, and the only thing I have left to solve for is I sub y, moment of inertia, about the centroidal y-axis. Other than that, I can use the exact same expression. I am going to tidy up this picture again. My recommendation is always to draw these things nice and large. That way you'll make fewer errors with your drawing. All right, there's 1 and 2. Here is my centroidal y-axis right there. There's my centroidal y. A lot of times I'll do like y, and that way I don't have to worry about which way is positive, which way is negative, because it doesn't matter in terms of the moment of inertia. Okay, so so IY or IYY, excuse me, we need to do the same operation before. So moment of inertia of shape 1 about its own parallel axis. Well, the parallel axis for shape 1 is that one. So I'm going to do a base of 1.5, a height of 3.5, cubit divided by 12. Moving on to term I2. Let's see. So I want this centroidal moment of inertia of that rectangle about its own centroidal axis. base of 3.5, height of 1.5 divided by 12. So base of 3.5, height of 1.5, don't forget to cube it, divided by 12. For my area times distance terms, I'm looking for the perpendicular distance between the centroid of the component and my y-axis, right? That's the one I'm looking for. Since this centroid and this centroid are coincident with that axis, that means that this is 0 and this is 0. So I don't have to use those terms. All right, that's always good news, right? So I'm going to do 1.5 times 3.5 cubed plus 3.5 times 1.5 cubed and divide that sum by 12. And there is my IY, 6.34 inches to the fourth. Again, kind of word of caution with these lengthy calculator operations. The only reason I'm not doing it twice right now is because I already know the answer. If I'm doing this on my own, I always double check. It doesn't take too long and you'll catch an error 1 time out of 10 or something like that. All right, on to the next problem. Problem 4. Determine the centroid of the eye-shaped cross-sectional area, then determine the centroidal moments of inertia. All right, I see 1, 2 lines of symmetry. So I don't need to waste time with my, X bar and Y bar calculations. I know that by inspection, X bar is half of 3.5. So I can go immediately to that answer. Okay, so by inspection, half of 3.5. My Y bar, the vertical dimension, is, line of symmetry. So half of the total height. So I've got 3, 4, 5, 6.5 total height. And divide that by 2 to get to my Y bar there. So we can do that one by inspection as well. Okay, so we've got that stuff done and we are ready to move into the next category. I'm going to toss that, I think I said that was 6.5 inches from top to bottom. And that's going to be useful in a minute, so let's put that there. Okay, let's do a moment of inertia about X. So what is IX? Well, we have to use the parallel axis theorem. So the summation of the moments of inertia of each component about its own parallel axis plus the summation of the products of the areas times distance of each of those components. Don't forget to square. Don't forget to square. Make sure I wrote that properly. Good. Okay. Okie doke. That is what we want to do. And for my x-axis, I see a shortcut. So if I used solids, I'd be using shapes 1, 2, and 3. But I see a shortcut if I use a solid shape, which I'll call 1, and void shapes. And I'm going to call these two shapes together, I'm going to call that shape number 2. You can call them 1, 2, 3 if you want, but I've got this nice symmetry going on. So I'm thinking of as 2. You could be like 2A, 2B, 2 left, 2 right, whatever floats your boat. All right, why am I doing that? I'm breaking it up into areas that all have a centroid that aligns to X. And that means I won't need any distance terms. So they're going to be 0 if I use solids and voids. If I were to use all solids, then I'm going to have distance terms to calculate. So I got to figure out that. I got to square it, multiply by area. Okay, so this way is going to be a little faster. Okay, Since we know our distance terms are 0, we can do I1 minus 2I2. I1 is a rectangle, so it's got a base of 3.5. It has a height of 6.5. Don't forget to cube it, divided by 12. Minus quantity 2, and each I sub 2. I'll go ahead and do it this way. That's fine. Let's see. I've got a 3.5 total width. 3.5 total width. And I need to subtract out this middle piece, which is 1.5. Okay, and then divide by 2. So on both sides, I have 1-inch base of the void and a height of 3.5 inches. Okay, so 1 by 3.5. So when I go to do my moment of inertia, base height cubed over 12, my base is my base is 1. My height is 3.5 cubit divided by 12. Okay. And again, spot check your units. So the same thing that I did before. So distance cubed, that gives me distance to the 4th. Distance cubed gives me distance to the 4th. So I am good to go with my calculation. All right, calculator time. So I'm going to divide by 12 last because it's common to both. And so I'm going to start at the beginning and say 3.5 times open parentheses 6.5 cubed equals minus open parentheses 2 times 1 times 3.5 cubed equals, and then divide by 12. And I get 72.95. That matches the answer up here. So when I want to keep that sig fig potentially for later, as in maybe I want to do a calculation with the principal moments of inertia later on, I'll usually use 72.95 inches to the 4th, say 73.0 inches to the 4th. And so that's saying, hey, this is my final answer for this part of the problem. And if I need that 4th sig fig of precision later on, I've got it jotted down so I don't ever have to come back and do this again. Just a little pro tip. You'll find in engineering calculations that oftentimes you need to go back and get this last sig fig. And it's annoying to have to do the calc again. Cool, that's IX. That one is done. And last but not least, let's do I sub Y. Clean up my picture again. Oops, wrong layer. Clean up my picture. And here is that centroidal y-axis. Y or YY, either one's okay. So sometimes you'll see people say YY for this. Means exactly the same thing, just a personal preference. Okay, look, goodness gracious, we have to do parallel axis theorem. So summation of the II plus summation of the AI distance, don't forget to square them. And we're good to go. Okay, so the centroid of the component parts, I'll call this one 1, I'll call this one 1, because they're the same thing. So 2 quantity shape 1, 1 quantity shape 2, but the centroid of all 3 of those parts lies on the centroidal y-axis. What does that mean? If I'm using these solids, I can eliminate my distance terms. So these are 0. Right, the distance from the center of 1 and 2 lies on the y-axis. So that simplifies things. So now I just have to do 2I1 plus I2. And that's a quantity 2. Okay, let's write it out. Moment of inertia of shape 1 about its own parallel axis. So here's the parallel axis. Base of 1.5. What are we going to cube? 3.5. Okay, moment of inertia of shape 2 about its own parallel axis, its own centroidal axis. So I'm going to do 1.5 and 3.5, and the one that I want to cube is the 1.5. Okay, calculator time, 2 times 1.5 times 3.5 cubed equals divided by 12. Oh, why did I do that? That's okay, I can keep going. Plus, open parentheses, 3.5 times 1.5 cubed divided by 12, and 11.7 inches to the fourth, which is the same answer here. All right, problem 4 is done. Let's go on to problem 5. By the way, I have noticed in class, some people really want to carry fractions through. And that can be helpful in some statics problems, such as concurrent force problems, any truss problems. Fractions are hugely advantageous. But for this type of problem, decimals is definitely the way to go. If you try to mess with the fractions, you're most likely just going to make some errors. So go with the calculator, go with decimals all the way for these types of calcs. All right, we have another cross section. This one is a C shape. A C shape. These are sometimes called channels. C shapes are sometimes called channels. And looking for lines of symmetry, and I see one here. So Y bar, which measures from here up to here, Y bar can be determined by inspection. I just need half of the total height. Total height is 6.5. Total height is 6.5 inches. Let me double check that. Yes, 6.5 inches. So half of that is 3.25. So we can get that one by inspection. Okay. And for my X bar that measures to my Y centroidal axis, unfortunately, I'm going to have to do this by calculation. So I'm going to eyeball my Y axis somewhere in that vicinity. And I'm going to put my centroid right there where those lines intersect. And I've got no choice, but I got to do the calculation for X bar. So we think back to our centroids and we're like, okay, X bar, it's like a weighted average times the total area. So A total, or summation of the areas, however you want to do it, is equal to the summation of the areas times the distance terms. And the distance terms in the centroid calculation are different than the distance terms in the moment of inertia calculation. Right, so if I'm doing an X bar calculation, that means I'm measuring in the Y direction. No, that's not true at all. I'm doing an X bar calculation, so I'm measuring in the X direction. So if you wanted to put that as X sub I, that is okay as well. And the summation notation, right? I mean, we usually just get lazy and just write the sigma, the capital sigma, but we could be more formal and say I equals 1 and count up to the number of component areas, if we wanted to do that. I'm going to give my component areas some numbers. So I have shape 1, quantity 2, and I have shape 2, quantity 1. X bar equals, so the denominator is going to be a little easier. So I'm going to say quantity 2 times area 1, which is 1.5 times 3.5, plus quantity 1, area 2, 1.5, 3.5. I could have just grouped this together if I wanted to, but that's okay. Times for areas times distances. So, goodness, 1.5 times 3.5. Yeah, let's go with that. So I'm just going to say, area 1 equals area 2 equals 5.25 inches squared. And in the numerator here, I have quantity 2 of shape number 1. The area is 5.25. And the distance is from our reference point to the center of that shape, which is half of 3.5. Okay, so that's quantity 2. This is quantity 2. The next term is the area and then the distance. And now we need to deal with shape number 2. Quantity 1, area 5.25, and distance from the left fiber to that centroid of that shape is half of 1.5. Half of 1.5. Okay, everything up top has units of inches cubed. Everything below has units of inches squared. So I'm on track to get the inches that I want. And again, while you're learning this, please, please, please write out, spot check your units, okay? So inches squared times inches. Inches squared times inches. Inches squared, inches squared. So just kind of validate and verify that all that is correct. Calculator. All right, I'm gonna do the numerator first. So 2 times 5.25 times 3.5 divided by 2 equals plus 5.25 times 1.5 divided by 2 equals divided by, open parentheses, and I'm just going to group them. So I'm going to say 3 times each area, which is 5.25. Just kind of simplify that. And that should give me the right answer. That did not give me the right answer. So, oh, no, it did. It did. Okay, awesome. 1.42 inches is the answer for X bar. With that information, let's update our picture. Simplify before we get into the moments of inertia. So X bar, so our centroid is here. And I do need that fourth sig fig for precision. Remember we talked about that? So on my picture, I'm going to keep that fourth sig fig, 1.416 bar. And while I've got that number in my calculator, I'm going to go ahead and multiply by -1 and then add 3.5 so that I can get this little chunk here, 2.083 bar. Okay, because I know that information is going to be useful to me as I go into the next stage of the problem. With that in mind, I will take this calc and actually the areas is useful information. So I'm going to leave the area, but all this stuff I'm going to make small and put it over here in case I need it later. All right, next up, moments of inertia. We'll do IX first. Parallel axis theorem is going to be needed, so I need the summation of the moments of inertia of each component about its own parallel axis plus the summation of the areas times the distance squared between the parallel axes. Here is my x-axis on the picture right here, so you could call it x or xx if you want to do. And in terms of our shapes, I'm going to do again 2 of quantity 1 and 1 quantity 2. Quantity of 2 of shape 1, quantity 1 of shape number 2. Okay, so I need 2I1 plus I2 plus A 2a1d1 squared plus a2d2 squared. Okay, moment of inertia, shape number one. We want about its own parallel axis. So that is parallel to that. Base of 3.5. We cube the 1.5. Moving on to shape number two. Just a reminder, this is a quantity, this 2 right there. Moving on to shape number two. Here is the parallel axis. And so we want to cube the 3.5. It's perpendicular to that. Now let's get into our areas times distance squared. 2, my area of A1 is 5.25 inches squared. And for the distance, I basically want to measure the perpendicular distance between the parallel axes. So from here to here is D1. Okay, what I'm going to do is take the total height of 6.5. I'm going to divide that by 2 to get this height. I'm going to subtract out half of 1.5. Okay, and that's going to be equal to D1. Okay, so what I'm doing is D1 equals total height 6.5 divided by 2 for the top half minus 1.5 divided by 2 equals whatever that is. I'll just punch it in a minute. All right, and we don't forget to square. Don't forget to cube. And we don't forget to square. It's our motto in engineering. Don't forget things. All right, there is my quantity 2, area 1, d1 squared. And for my last one, a2 d2 squared, well, the area, a2 is 5.25 inches squared. And my distance term, so the centroid of shape 2 shares the same axis as what we're looking for, which is x. There is no perpendicular distance between the axes. So this one is 0. And I guess that's the exception to the rule that you don't really have to remember to square 0. That term all goes away. Right, calculator. How am I going to do this one? Let's see. I'm going to do this one first. I usually do the most complex term first, and then the ones that are more straightforward after that. So I'm going to kind of work backwards. So I'll do 6.5 divided by 2 equals minus 1.5 divided by 2 equals square it times 5.25 times 2 equals plus, and I'm going to do the term in the middle now, 1.5 times 3.5 cubed divided by 12. Okay. And then the final term, the one in the front, plus 2 times 3.5 divided by 12 times, open parentheses, 1.5 cubed. All right. And 72.95 matches our answer up here. Inches to the 4th. All right, one more to go. One more to go. Get this calculation and make it small. Put it over here. And all I need to do is change my parallel axis theorem to go for an IY instead of an IX. And I'll clean up my picture just a little bit. So our centroid is here. And we're interested in the moment of inertia about the y-axis or yy. All right, goodness. I don't really see an advantage in using voids, so let's just use solids for this one. So I'm doing quantity 2 I sub 1 plus I sub 2 plus quantity 2 quantity 2 A1 D1 squared plus quantity 1 A2 D2 squared. All right, moment of inertia of shape 1 about its own parallel axis. So here is the centroid, and there is that parallel axis. So I'm going to do BH cubed over 12, base of 1.5, height of 3.5, cubit divided by 12. Next term, I sub 2. There is the centroid of shape 2. There is its parallel axis. Base is 3.5. Height is 1.5. Don't forget to cube it, all divided by 12. Okay, next term, 2. My area is 5.25. We did that a little earlier. Saves me a couple clicks in the calculator. And D1 squared. All right, so I want to figure out this small dimension between the overall y-axis and the parallel axes of shape 1. All right, how are we going to do that? I think what I'm going to do, take this distance from here to here. That is equal to half of 3.5. And then if I subtract out this distance, 1.416 bar, that will give me this little distance, d sub 1. Don't forget to square it. All right, we've got one more term to go. It's gonna make this just a tiny bit smaller, so I've got a bit more room. Last term, my area number 2 times distance 2 squared, area is 5.25. But what is my D2? What is my D2? All right, so my D2 measures between the overall y-axis and the parallel axis of shape 2. Okie doke, so that's what I need. How am I going to figure that out? Well, I know that this little dimension right here, that one's got to be 1.5 divided by 2. And if I deduct it from this dimension, then I'll get d sub 2. So here's my logic. D sub 2 is equal to 1.416 bar minus 1.5 divided by 2. So I'm going to put that down here in the parentheses, and I'll just do one little simplification as I go. All right, 1.416 bar minus 0.75, and don't forget to square it. All right, another big mess for my calculator. I'm gonna work from right to left. So I'm going to start with 1.416, and I usually just kind of put a few more in for good measure. It's really not mission critical, but minus 0.75 equals square it times 5.25. Okay, add to it the next term, open parentheses 2 times 5.25 times open parentheses 3.5 divided by 2 minus 1.416666, and I want all that squared. I'm going to look at this one real quick and make sure it looks good. Looks good. Enter. Lastly, plus, I have 2 more to go, so I'll do 3.5 times 1.5 cubed divided by 12 plus 3.5 cubed times 1.5 times 2 divided by 12 equals. And we do get to the final answer of 15.2 inches to the fourth. All right, so you're watching the solution video for this, so it probably means you had an error to catch. And my hunch is it was one of these things, if I was going to wager some dollars. You forgot to cube something, or you messed up this calc or this calc. That is my official wager for what went so wrong. Those are by far the most common errors. All right, 2 more to go. On to problem 6. We have an oddly shaped cross-section, and we want to figure out x bar, y bar, centroidal moments of inertia. And since this cross-section does not have a line of symmetry, now we get to also do the product of inertia. And what I'm going to do for this, goodness, I've worked this problem before, and feel like it's a big advantage if we can make this a little bit bigger. I'm going to keep the answers, but make them a little smaller, put them here. Get rid of this stuff. And put this up at the top. Okay, I think that looks big enough. All right, let's start with our X bar. So we need some shapes, and looks pretty reasonable to do 1 and 2 and put in centroids of each one. X bar is equal to the summation of the areas times their distances over the summation of the areas. First term, A1, D1. First area, base of 2, height of 3. Distance from here to here is half of 2, or 1. Next term, area 2 is a 1 by 1. Area 2 is a 1 by 1. And its distance, we start over here and measure this way. That's equal to 2.5. Okay, so 2 times 3 and 1, 1 and 1 and 2.5. In the denominator, I have 2 times 3 is 6, plus 1 times 1 is 1. Calculator, 2 times 3 equals plus 2.5 equals divided by 7 equals 1.214. All right, and we're going to want to keep all 4 of those sig figs in the subsequent steps. this up here in case we need it later. Next up, we will do our y-bar calculation. We want the summation of the areas times the distances in the y direction divided by the summation of the areas. In the denominator, we already know our total area is 7 in inches squared, so I'll put it down there. Up top, my first area 2 by 3, so that's 6, and I need a distance. My second area 1 by 1 is 1, and I need a distance. For shape 1, I measure from the bottom fiber up to here. That's half of 3. So I'll put 1.5. And for shape 2, measure from here up to here. That's 2.5. 6 times 1.5 equals plus 2.5 equals divided by 7 equals 1.643. Okay, so we're going to run with that. Now we're ready for moments of inertia. Let's go ahead and get the centroid in there and drawn pretty well to scale. So I think what I'm going to do, here's what I'm going to do. I'm going to go into this layer and try to draw this pretty precisely. So otherwise this drawing is going to get kind of messy. All right, X bar 1.2. Let's try to draw this one to scale. Put it, there's 1. So 1.2 is something like that. Well, all I have, oh, I've got the 1.64. All right, I'll come and do this in a minute. Figure out what that is. Okay, Y bar 4.012. That's totally not right. Y bar was like, that doesn't make any sense. Y bar equals 1.643. All right, there is 2, so there is 1. There is 1.5. 1.6 is right. Let's kind of put it there-ish. Those are my centroidal axes. Here's my overall centroid. There is X. There is Y. Here to here, we have 1.643. And while I've got that in my calculator, I'm just going to subtract 3. Change the sign, but whatever. 1.357. And at the bottom, I want to say 2 minus 1.214. And I'll get 0.786. Okay, of course, these are all inches. Okay, that is where we are at to start off this party. Let's get back to the foreground. Oh, let me do one other thing. So I'm going to call this one shape 1. The little one will be shape 2. Back to the foreground. Our next task is to calculate IX. And I think I'm going to do this in trying to decide if I want to do a tabular format or not, because I have to do the product of inertia. I think I'll just do it with straight up equations for this one. Sometimes I do it as a table. All right, moment of inertia about the centroidal x-axis, parallel axis theorem, summation of the ii's plus summation of the aidi squareds. And for x-axis, so here are our parallel axes, this one and that one. So I is going to be, I'm sorry, I1 plus I2 plus A1 D1 squared plus A2 D2 squared. Okay, I1 is base of 2, height of 3, cubit divided by 12. I2, base of 1, height of 1, cubit divided by 12. Area 1 is 6. Distance 1 is something. Area 2 is 1. Distance 2 is something, and we have to remember to square it. All right, let's get our distance terms off of the picture. So the distance, the perpendicular distance between the parallel axes of shape 1 and the overall x-axis is as shown. I'm going to determine that by looking at this measurement and subtracting out that measurement, which is half of 3. That again, long video. I need a break. 1.643 minus 1.5. Okay, so that looks good. I'm going to leave this dimension. You want to know what I'm going to do actually? Oops, throwing on the level layer. That's kind of embarrassing. Okay. Use your imagination. Since I know I'm going to have to do the product of inertia coming up, I'm going to have to calculate this again. So I'm just going to label it very clearly. So I've got 1.643 minus 1.5. So 0.143 inches is there. Right, now we move along to this second distance. So that's D2. D2, we have to square it. And distance 2 measures between these two parallel axes. To get that, no. These two parallel axes, okay, so the parallel axis of the component and the overall axis, which is the one that we actually want to solve. Okay, how are we going to figure that one out? I'm going to take 1.357, 1.357, and I'm going to subtract out half of 1.5 equals, and so I know this distance is 0.857. 0.857. Okay, ready to do my calculator operation. So I'm going to go ahead and square what's in there. Multiply by 1 plus 6 times 1.643 minus 1.5 squared plus 1 divided by 12 plus 2 times 3 cubed divided by 12. And I've got my IX 5.440 right there. As before, I'll take this calc and make it small. Just in case we need it later. Now we need to do IY. We need to do our IY. Parallel axis theorem. Summation of the II's plus summation of the AI DI squared. So for us, it's I1 plus I2 plus A1 D1 squared plus A2 D2 squared. And Now we're doing y. So I get kind of fixated on this as I think through this. And here are the parallel axes, the one and that one. So just add that, add that. Okay, I sub 1 about its parallel axis, which is this one. That means for the base, I use 3. For the height, I use 2 cubit over 12. I2, it's still 1 cubed by 12. Squares are nice because you don't have to figure out which one to cube. Area 1, 2 times 3 is 6. Distance 1 squared, we need to figure that out. Area 2 is 1 by 1 or 1 inch squared. Distance 2 squared, we need to figure that out. Okay, so distance 1 is this dimension right there. And to get it, I'm going to take 1.214, and I'm going to subtract out half of 2, which is 1. So I'm going to get 0.214, 0.214 for shape 1. On to shape 2. Now I need this distance from the parallel axis to the axis I'm interested in, which is y. And I'm going to take 0.786. And to that, I'm going to add this distance, which is half of 1. $1.286. Okay. More math. 1.286 squared plus 0.214 squared times 6 plus 1/12 plus 3 divided by 12 times 2 cubed. And I get up to 4.012. IY is done. Okay, next thing we're asked to do is the product of inertia, which is called I, X, Y. And our formula for this one is the summation of areas, the X coordinate, the Y coordinate, and we have to watch signs. So in every other type of moment of inertia calculation, we were squaring a distance. So we did not have to track negative signs because we were squaring whatever that was. Just don't bother, just write it as a magnitude. But here, this gets a sign, this gets a sign, so their product could be positive or negative, and we have to carry those signs through. All right, let's go ahead and do it. IXY equals A1, X1, Y1 plus A2, X2, Y2. Area 1 is 2 times 3 of 6. X1. To go from my centroid to the center of X. Let me say this again. To go from my overall centroid right there to the center of shape 1, I have to go negative 0.214 inches. To go from my centroid to the centroid of shape 1, I go negative 0.143 inches. So the negative signs will multiply and turn into a positive in that term. Area 2 is the 1 by 1, so 1 inch squared. X2. So you could think of these really like an ordered pair. So it's like if I start at the overall centroid C, and then I go this distance and this distance, I go positive, positive. 1.286 in the X direction, 0.857 in the Y direction. That's all there is to it. Multiply 6 times 0.214 times 0.143 equals plus 1 times 1.286 times 0.857 equals. And we get up to our product of inertia here. If you look earlier in this lesson on the website, you'll see that I've actually done the Mohr circle example with these numbers. Okay, so feel free to look at that if you'd like to take this problem to the next step. All right, one problem left. Problem 7, and this is a Mohr circle problem. There is a solution by another professor, but we'll do our own here. All right, so Mohr circle for moment of inertia. We have two different axes. On the horizontal axis, I want to plot the moment of inertia about the centroidal x-axis, the moment of inertia about the centroidal y-axis, or any other axis, A, B, C, D, what have you. The vertical axis, I want to plot the product of inertia IXY. There is an IXY right there. We begin the process by going into the circle with 2 points. My point labeled X is going to be IX, IXY. So IX is 160. IXY is 40. Okay, this is all in inches to the fourth. All in inches to the fourth. My y point, I just do IY comma negative IXY equals 100 comma negative 40. Now, Mohr circle is an abstract tool, and it's one of these things in engineering classes that it doesn't make sense until it does make sense. And once it clicks for you, it's a wonderful thing, but it is perfectly normal to have trouble figuring out what this tool is all about until you practice it enough where it starts to make sense, okay? So you're just starting out with this, so just kind of go for the ride, try to understand. Don't worry too much if you're not getting every nuance here the first pass through. All right, let's plot our points. So this is one where, let's see if I can get a dot pattern here. Let's see how this works. That's not bad. This is one where a little bit of drawing to scale is useful. So for my X, I'm going to make each one of my dots worth 10 inches to the fourth. So thinking ahead, I know I'm going to have 1, 2, 3, 4. So that's going to be a product of inertia of 40, kind of along this line. And then 1, 2, 3, 4, a product of inertia of negative 40 along this line. Okay, so just kind of thinking ahead and starting to draw a scale. So 40 and -40 down here. Okay, and I'm going to need 100 and 160. So, okay, so 100 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 1, 2, 3, 4, 5, 6 for 160. Okay, let's plot the points. So 160, 40, that gets me to x. There's my 0, there's my 0, 0 right there. 100 minus 40 gets me here. Okay. With this information, we're ready to start working through this circle. I'm going to zoom in and we'll work through this really organically. So my center of the circle is halfway between 160 and 100. So I just average 100 plus 160 divided by 2, 130. Another way to report this, you could also just write C equals 130, 130 inches to the fourth. What does the center mean? Not a whole lot on its own. Not a whole lot on its own. It's just one intermediate step in this process. Next, we get to do a little bit of trigonometry. If I find this triangle or this one, they will always be the same triangle. They will always be the same triangle, and they'll always have 40 as this vertical piece here. And we need the base of the triangle. So I could take 160 minus 130 to get 30. Or I could take 130 minus 100 to get 30 for this one. Okay, either one will work. So it looks like I've got everybody's favorite triangle, the 3, 4, 5. So my radius scales to 50 inches to the fourth. Now we get to draw our circle. So we start at the center, and I'm at a center of 130. And if I increase by the radius, so I add 50, I get to 180. So that should be there. Okay, so this is going to be called I max 180, or center plus radius. And to go leftwards, I would again start at my center 130, but now subtract my radius of 50, and that gets me to 80. Right there. That is my minimum moment of inertia. Right there. Honestly, that's the main stuff you need from this Mohr circle. This is the simplest type of Mohr circle. But let's go ahead and fill it out. So radius is 50, 1, 2, 3, 4, 5. There's my top quadrant. 1, 2, 3, 4, 5. There is my bottom quadrant. And for my circle itself, I just kind of connect the dots. And if I've drawn it to scale, it should make a circle-ish. That wasn't my best work. I'll try that again. Okay, close enough. Close enough. All right. The main other thing we're going to do with this more circle is try to figure out if I want to go from native or input moments of inertia with respect to X and Y, how do I rotate that in real life to get to I min and I max? So what we're going to do is put our hands on the steering wheel. I'm going to pretend like we're driving a car. We're going to grab X and we're going to make a right turn to put X over here. And at the same time, we're going to grab Y, hands on the steering wheel like you're driving a car, and we're going to turn over there. So what I need to do is determine what these angles are. Okay, what are these angles in the circle? And then remember that in real life, they're always exactly half. So I'm going to just, I'm going to make this just a touch bigger. So I'm going to take, see this triangle right there? I'm just going to redraw here. And in the circle, 2 theta p defines this rotation, this coordinate transformation we do from our given x and y to what we want to get, which is I max and I min. So if this is 40 and this is 30, then I would just say tangent of 2 theta p equals opposite over adjacent. That's 40 over 30. So 2 theta p equals inverse tangent of 4/3. And theta p, that's the rotation in real life, is equal to half of that. Okay, so check my calculator. It looks like it's in radians, so let me fix that. Okay, these are usually reported in degrees. By the way, you can always look at the top of the calculator here, right? It says it's on engineering notation floating, so I'm getting all the digits. I don't know what that auto is, but real is real numbers and degree versus radians are here. So it's good to check in there. Let's go ahead and do an inverse tangent of 4 divided by 3. So that tells me that 2 theta p is 53.13 degrees. And I kind of eyeball that in the circle, and does that look like about 53 degrees? Yeah, it does. More than 45, less than 90, close to 60, so that makes good sense. And then just divide by 2 to say in real life, my angle is 26.56 degrees, say 26.6 degrees. Now, these things also have signs, and the signs is, it's always a trick question for people who teach this. It'll catch so many students off guard on this. So, which way did I turn the steering wheel? I turned the steering wheel clockwise. And so you're going to report this answer either with a little curly arrow like this. That's the way I'd rather see it. Or you could say negative 26.6 degrees. That would be okay as well. But you do the sign by inspection. Lastly, to finish up the problem, we want to do a sketch. And in this problem, we don't know what our area looked like, right? We were just given the information. So we had some random area, and we had centroidal axes, X and Y, and blah, blah, blah. But now we know to get to our principal axes, we need to rotate 26.6 degrees clockwise. So 26.6 degrees clockwise. 26.6 degrees clockwise. That's going to give you your new axes. So this one, and goodness, that's not a very good 90-degree angle. Let's just do it like that. Okay, fudge that a little bit. So we keep the same centroid, but now we have new axes. We could call this AA, we could call this BB. And what Moore's circle tells us is that the largest moment of inertia that we can have is located at 26.6 degrees clockwise from that x-axis. So I max of 180 inches to the fourth is the moment of inertia about this axis. I min, which we calculated to be 80, is about what we're calling axis BB. And the names of the axes, some people use like U and V, some people use I and J, some people use X prime and Y prime. It doesn't really matter what you call them as long as you know how to interpret all your Moore circle results. All right, that's it for this homework set. I hope this video was extremely useful to you, and I hope you have a fantastic day.